In this section, we're going to talk about differentiability and continuity. I actually like to do continuity first. So we're going to say a function is continuous if there are no breaks or gaps in the function. Or you could think about it as you could draw the graph without picking up your pencil. So here are some examples. We want to see, is the function continuous at x equals 3? So in this first one, notice this is my function, y equals f of x. But notice right at this x equals 3, they put what we call a hole. They put a hole right there. And the actual function is defined up above. So everywhere else, we have this nice graph, but at the actual point x equals 3, f of 3 is defined as 4, and so it's kind of this point up above. There are some practical applications for why you would see things like this. Usually we have what's called piecewise functions. Okay, but in this case, it would be, no, not continuous, because I would have to pick up my pencil to put a point way up here. In this next one, this is what we call a piecewise function. So this was a hole. This is a piecewise. And the pieces don't match up. Okay, so we have a piece that comes down here, but my other piece is up here, so I would have to jump. So piecewise, it doesn't match. Okay, so it's not continuous. I have to jump way up here to start my next graph. In this example, notice we have a vertical asymptote. Right here, here's my asymptote. And so coming up this side, my graph goes up to infinity. This side comes up to infinity. But we never actually cross this line. There is no point right at x equals 3. So vertical asymptote. And so not continuous. And finally, look, we have this nice graph here, but right at x equals 3, we have another hole. So it is not continuous. Notice at this point they didn't even tell us where the other point would be. It's just an empty missing hole. On this next graph, if we look at x equals 3, I don't actually see anything wrong there. There are no holes, there are no jumps, there are no breaks, so this one would be continuous. And for the most part, all I'm going to be having you do is look at the graph and say, does that look continuous, yes or no? But we might do one or two problems where I actually ask you a little more officially if a function is continuous. So officially, a function f of x is continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. This means you actually check three things. First of all, make sure your actual function is defined at x equals a. Make sure you don't just have a hole there. Next, make sure that your limit actually exists. And 3, make sure that your limit matches your actual point. So all of these things have to happen. So let's try it. In this example 3, it's f of x. Notice this is what we call a piecewise function. So f of x is equal to x plus 2, that's this line right here, from -1 to +1. Then it's equal to 3x from 1 to 5. So this is a piecewise function. We want to see if it's continuous right here at x equals 1. Now you could just look at your graph, and looking at that graph, I would say there are no gaps, no jumps, nothing weird. So this would be continuous. Let's actually do it theoretically though. Let's see, what is actually f of 1? To find f of 1, I say, where is 1 defined? So they actually define 1 right here on the top function. So let's plug in 1 there. So 1 plus 2 equals 3. Okay, now let's find the limit. So when we look at limits, we have to see what are these numbers approaching, and we want to check from the left and right to make sure that they match up. So the limit from the left, okay, you can look at your graph. As I come from the left, I'm getting closer and closer to 3. Or you could plug 1 into your top function because that's coming from the left. So 1 plus 2 equals 3. And let's check it from the right. Limit from right means plug it into now your bottom function. So 3 times 1, which equals 3. So the limit, as long as it's the same from both sides, we can say the limit as x approaches 1 of f of x equals 3. Okay, so we found that, yes, f of x is defined at 1, it's 3. We found that the limit also exists, it's the same from both sides, and it is 3. And finally, both of those numbers are 3, so they match. The limit as x approaches 1 of f of x is actually equal to f of 1. So everything held, and this is continuous. Again, in this class, I'm mostly just going to have you look at the picture, but you will do one official problem where you actually check it out like this. Okay, now there's something different called differentiable. So we say a graph is going to be differentiable if you can actually find the derivative or the slope at x equals a. Okay. Now I say derivative or slope because remember the whole point of derivatives is that they tell us the slope at a point. So let's look at some of these graphs. Okay, in this first graph, notice we kind of have a sharp bend. Okay. So most of these problems are going to have sharp bends. Okay, and so remember we're trying to find the slope. If I was to look at this problem coming up here, coming from the left, my slope is positive. But from this side, my slope is negative. So this has a positive slope, this has a negative slope. What are you going to tell me is the slope right at this point? It gets confusing. Should it be positive? Should it be negative? It changes right there so quickly that we can't find the slope. Okay, and on this graph, okay, notice again, my slope changes so quickly that we can't actually find a slope. You can't find a tangent line. Remember, a tangent line is supposed to kind of match your graph. If you zoomed in really, really close, it would match your graph. So like right here, if I was to try and find it at this point, I'd have a tangent line that looks like this, and if you zoom in enough, it matches your graph. But how will you find a tangent line that matches your graph right here? If I drew a flat line like this, that doesn't seem to match right there, and it doesn't match right there. It doesn't really match at all. There is no tangent line. It just doesn't work. Okay, or again on this graph, notice again it's a sharp bend. Okay, so all three of these are a sharp bend. So anytime you have that sharp bend, the slope changes so quickly that we can't find the slope right at x equals a. Okay, and so all of these would be non-differentiable. We can't find the derivative there. We can't figure out what the slope is at that point. And also on this one, notice right here on this graph, we could actually kind of figure out what the tangent line would be, but it's a vertical tangent line. Vertical tangent lines, remember, or vertical lines have undefined slope. So if it's undefined, it's not actually a number, which means we can't actually find the derivative. So all of these are non-differentiable. So if you're looking for non-differentiable, you're going to look for vertical tangent lines or places where you have a sharp bend. Everywhere else on these graphs was just fine. You could find the derivative because you could figure out the slope, but not at those points. So if you wanted to check if a function is differentiable, doing it more mathematically. So again, if you want to see if it's differentiable, what we're going to do is see if we can find the slope or the derivative at that point. Or if it's something like a piecewise function, like this where the function changes, you want to find the slope from both sides and make sure that it matches. So this example, this is the same function we already looked at. We saw that it was continuous. Now let's see if it's differentiable. Okay. So I can see just looking at it that that's going to be a sharp bend. Or my slope changes drastically at that point. But let's actually check. Let's see, what is the slope from the left? So from the left, it's going to be that top function, x plus 2. And you know how to look at a function or a graph of a line and see what the slope is. Just what's the number in front of the x. So slope would be 1. But our slope from the right, the number in front of the x is a 3. So those don't match. So the slopes don't match. Okay, or there's a sharp bend. We can't actually find the slope at that exact point because it's changing so quickly. So this function would be not differentiable. Okay. And just a final, very theoretical remark is that all differentiable functions are continuous. So if you're going to have something where you can find the slope at every point, there are no sharp bends. That also means if you can find the slope at every point, there are no holds, there are no jumps, there's nothing going on that's weird. So all differentiable functions would be continuous, because if you can find the slope at every point, your function would also be defined at every point and match up. But the opposite is not true. Not all continuous functions are differentiable, so we just looked at one right here, this function. It is continuous. I don't have any jumps or holes or anything, but there was that sharp bend, and so I couldn't actually find the slope at that point, and it was not differentiable.